First question, the internal energy of an ideal gas increases during an isothermal process when the gas is. So first of all, we know that internal energy U is equals to F upon 2 mu RT. Now we know that mu is equals to number of moles upon Avogadro's number. So that is F upon 2 N upon Na into RT. Now looking at this equation, we can see that F upon 2, Na and R is constant. So we can say that internal energy U is directly proportional to number of molecules and T, that is temperature. But the question is asked for isothermal process. So we know that for isothermal condition, T is equals to constant. And therefore in this equation, now I can say that U is directly proportional to number of moles. That means the U, internal energy, increases by increasing the number of molecules, and therefore the internal energy of an ideal gas can be increased by adding more number of molecules to it. So the correct answer is option A. Now, moving towards the next question. A gas undergoes a change of state during which 100 joule of heat is supplied to it and it does 20 joule of work. The system is brought back to its original state through a process doing 20 joule of heat is released by the gas. The work done in the second process is what you're supposed to find out. Now we know that in a cyclic process, delta U is equals to 0 and therefore delta Q is equals to delta W, which means Q1 minus Q2 is equals to W1 plus W2. So first of all, we need to find out what is Q1, Q2 from this question. So Q1 is 100 joule, W1 is 20 joule, Q2 is 20 joule, and W2 is what we are supposed to find out. So putting this in the question formula, we get 100 minus 20 equals to 20 plus W2. And we find that W2 is equals to 60 joules. 100 minus 20 is 80. And this 21 comes over here. That gives you 80 minus 20. That is 60. So W2 is 60 joule. Correct answer among the given option is option A. That is 60 joule. Next question. N moles of an ideal diatomic gas are in cylinder at temperature T. Suppose on supplying heat to the gas, its temperature remains constant, but N moles gets dissociated into atoms. Heat supplied to the gas is. So for this, since we know the gas is enclosed in a vessel, therefore during heating process, volume of gas remains constant. Hence, no work is done by the gas. If it means heat supplied to the gas is used to increase its internal energy only. So from this we find out that U1 is equals to N into 5 upon 2 R into T. Now since N moles get dissociated in this process into atoms, so after heating, vessel contains total number of moles N minus N which is dissociated. So this N minus N is the moles of diatomic gas and 2N moles of monoatomic gas. So now my second condition of internal energy U2 will be equals to N minus N into 5 upon 2 R T plus, this is diatomic, so it's 2N 3 upon 2 R into T. When you do this calculation, we find out it's equals to 5 upon 2 nRT plus 1 upon 2 small nRT. And thus, the correct answer by using U2 minus U1 is equals to this term or this equation minus this equation, we get 1 upon 2 nRT, because this is nothing but 5 upon 2 nRT. So this will get cancelled out with this and only term left in the equation is this. So the correct answer among the given option is option B, that is 1 upon 2 nRT. Next question. When an ideal diatomic gas is heated at constant pressure, the fraction of heat energy supplied which increases the internal energy of the gas is. Now the fraction of supplied energy which increases the internal energy is given by this fraction F will be equals to delta U upon delta Q, that is heat change at constant pressure. This can also be written as delta Q at constant volume, that's internal energy. And this is written as it is, delta Q at constant P. Now this delta QV and delta QP can be written as mu into CV delta T the whole upon mu into CP delta T. This mu get cancelled, delta T get cancelled. CV upon CP is nothing but equals to 1 upon gamma, because gamma is equals to CP upon CV. So this is 1 upon gamma. Now we know that for diatomic gas, gamma is equals to 7 upon 5. So the fraction, the fraction of the heat energy supplied which will increase the internal energy of the gas is given by 1 upon gamma, that is equals to 5 upon 7. So the correct answer among the given option is option D, that is 5 upon 7. Moving towards the last question. Two cylinder A and B fitted with piston contain equal amount of an ideal diatomic gas at 300 Kelvin. The piston A is free to move while that of B is held fixed. Free to move, and this is fixed. The same amount of heat is given to the gas in each cylinder. If the rise in temperature of the gas in A is 30 Kelvin, then the rise in temperature of B is equals to what? Now in both the cylinder A and B, the gases are diatomic. So therefore, gamma will be equals to 1.4. Piston A is free to move. So therefore, piston A will be, or the system A will be isobaric process. And piston B is fixed. So it will be isochoric. If same amount of heat is supplied to both, then delta Q isobaric is equals to delta Q isochoric. Now, delta Q isobaric can be written as mu Cp delta T of A. and this is mu Cv delta T of B. Mu get cancelled. Now this 2 is remaining, Cp delta T of A, which is equals to Cv delta T of B. Okay. We are supposed to find out what happens in the rise in temperature of gas in B container. So therefore, delta T B is taken at one side and rest all on the opposite side. So we get Cp upon Cv into delta T A. Now we know that Cp upon Cv is equals to gamma. So therefore this is equals to gamma into delta T A. Now in the question initially we know that for the diatomic molecule gamma is equals to 1.4. So I can put it simply here. It's 1.4. And the change in temperature in the A container is 30 Kelvin. So I'll put it here as it is 30. Now multiplying this we get 42 Kelvin. So the correct answer among the given option is option D, that is 42 Kelvin. So the rise in temperature of the gas in B is 42 Kelvin.